Yeah, so this is a work with Philip Hauke, who is my postdoc mentor, and Alessio Pavigalanti, who is a master student, and Philip Rory, who is a PhD student. So we study out of equilibrium universal dynamics of Sachdev-Ye-Kitaev model. So first, for the sake of completeness, let me introduce the model. So it's a zero-dimensional model of complex fermions, spinless complex fermions, which has all-to-all disordered interaction. That is to say that the interaction strings, so it is only interacting model, it doesn't have the hopping part. So the interaction strength, these J's are Gaussian random variables, which has variance if it if the diagonal elements has the twice the variance of the off-diagonal elements. And yeah, so the model is even though I am going to present for complex fermions, but it's been studied quite extensively with respect to Majorana fermions, and there are variants for hardcore bosons, spins, etc. Thing is, we mostly study for different Q values, the subscript Q values of the SYK models, but mostly I will discuss results for SYK4, which is a two-body interacting complex fermions with disordered interaction. So, in contrast to the Majorana model, this model has conserved charge, charge density, and the results which we shall see today is in the half-filling sector of this. There are many experimental proposals and attempts have been made to realize this model in quantum matter systems such as graphene flakes, optical lattice, superconducting qubits, wires, and quantum dots, and so on. So why this model is so interesting, that let me first give you a glimpse of that. This is exactly solvable model. So through saddle point method, you can get an exact solution of it at large n, and the model doesn't have quasi-particles excitations, unlike the normal Fermi liquids. So this stands as a model for microscopic model for strange metals. Okay, again, this the level spacings of this model, the lowest level spacings are exponentially suppressed with respect to the system dimension or the system size, in contrast to 1/n level spacing for normal Fermi liquid systems, which allows us to employ the eigenstate thermalization hypothesis throughout the entire spectrum, even at the bottom of the spectrum or the top part of the spectrum. So, well, this is an extremely chaotic model in the sense why I'm saying it's very extremely, because it satisfies a bound given which measures the chaoticity in a model, which is given by these out of time order correlators, and the true out of time order correlators actually is exponentially decaying, and the rate with which it decays is given by the Lyapunov exponent, and there is a bound of this how large this Lyapunov exponent can be is given by this the inverse temperature of the system, and this model is found to saturate this bound at low temperature, which also is the case for charged case for the black holes, and this model has a nice area safety duality or a two-dimensional charged black holes. So in that way, this model is very interesting, but for a quantum matter point of view, we have a model which is extremely chaotic, but we can exactly solve that model. So this model has become quite interesting to study in recent days. Now let us go to the point where what we have started in this for this model. So we considered a quench, and we see the dynamics after this global coinage has been made. So for convenience, we choose the global coinage from Fermi-Hubbard model to the SYK4 model. But we emphasize that the initial states which we choose from the Fermi-Hubbard model for different interaction and the hopping ratio, that need not be the case. We can choose any generic initial states, and the results which we shall see today follows are quite applicable for any initial states. So yeah, so what we do is like we far from a global coins from Fermi-Hubbard to SYK4, and the model we simulate the model exactly under this SYK4 Hamiltonian. Okay, as an observable, we consider the quantum Fisher information first of all. So which is nothing but for a pure state is the variance of an operator, and for convenience of our, I mean, we have chosen different operators, but for convenience, I show the results for the staggered magnetization here. Since we considered spinful Fermi-Hubbard in one hand and then spinless SYK4 in the other hand, we mapped the spin degrees of freedom to the spatial degrees of freedom, if you think of, or the different modes of zero-dimensional model. So in this form, where the odd spins are considered as the downspin are considered as the odd sides, and off spins are considered the even sides. So what do we observe? We see the quantum Fisher information for different symmetry unbroken Fermi-Hubbard initial states decay with time under the SYK4 Hamiltonian. These are the disorder average quantum Fisher information, and goes to a steady state. The different colors corresponds to the different initial states of the Fermi-Hubbard models with increasing contrast, or the darkest is the interacting one, and larger is the interaction, lighter is the setting. And the steady state, which is denoted by these dots, is or the parallel horizontal dots that corresponds to the infinite temperature value of the observable. Okay, so what we can observe, okay, we perform a simple risk scaling. That is to say, we subtract the steady state value or the long-term average value with a scale factor which is shifted by the initial value of subtracted with the long-time average value. And if we do so, this simple risk scaling, we see that all the curves collapse on the top of each other. Even more, we can fit this rescaled curve with a simple Gaussian, and we see that it's the dynamics is quite fast, which is reminiscence of the fast scrambling nature of this model. All right, so these observations are also applicable for other observables. For example, we have considered these spin flip observables here, and we not only consider this variance, right? We can compute for the different movements of this observable we have considered, and we see that at least for the staggered magnetization, it is the even moments which starts from 0 and remains at the finally totally mixed state also, it is 0. So it just fluctuates around 0, whereas the for the even moments, they show the dynamics which I just explained for the quantum Fisher information. And the similar dynamics we see for other SYKs like 2, 6, and 8, which we have so far computed. All right, in order to understand what's going on, we formalize one formalism which is based on the disorder averaged von Neumann equation. So we wish to compute the dynamics of the disorder average density matrix. So forget about the SYK4 model now. This is applicable for any generic models. We have a Hamiltonian, and which has a clean part, and we have a disordered part where each has the Hermitian operators. And So this, for example, in this SVK4 model, this random disorder, the stochastic parts are Quain's disorder, so they have infinite correlation time. However, it is applicable for any type of correlated disorders. Okay, so yeah, so our aim is to compute the ensemble average von Neumann equation. So we have to then compute these ensemble average of the density matrix with the different random variables or the processes. Okay. So for that, what we do is we see that, okay, the density matrix itself is sorry. Thank you for the reminder. Itself is so I'll go fast. Density matrix itself is a functional of the different random variables. We employ the Novikov-Furutse theorem, which allows us to write down this part in terms of the correlation or the correlations of these random variables, and in terms of the functional derivative of the density matrix. Then, in order to compute this functional derivative, we go to the formal definition of the formal solution of the von Neumann equation, and which can be casted in terms of this by substituting it. We can cast it as a functional derivative of infinite series. Okay, and yeah, so we truncate it to the first order just to see what's going on, how the result. So we get a form like this, which is also, I mean, in the double commutative form, which also sort of decorrelation and the Boré approximation one can think of. Furthermore, we perform a Markov approximation in order to cast that equation, double commutative equation, in terms of the time local form. And if we do so, then we just do a massage to this double commutator. We get the standard master equation of the Lindblad master equation form. Okay, so what we have so if we don't, so we have a coherent part and we have a dissipative part, but this dissipative part is not arising due to some empowerment. Rather, it is governed by the ensemble averaging and the correlation correlators, and the strengths are given by the correlations of the random processes. And this also shows us that, okay, we have a steady state which is maximally mixed. Okay, we apply this formalism for SVK4 model, so I will just quickly go through it. We don't have the clean part. We make the disordered part in terms of the Hermitian operator. If we do so, and this correlation tensor we now have is the variance of the different random variables, and from this time integral, then we get a Gaussian form of this of the evolution. Okay, so so the rate dashed curves are from the master equation, whereas the greens are from the exact dynamics, and we see that's quite a nice agreement from the master equation formalism and from the exact dynamics. So yeah, so most of the features of this evolution have been captured, but some of in the intermediate domain we don't have this overlap, but that we can consider coming from the truncation we have done and the Markov approximation. Furthermore, we do in order to understand the universality, we do a spectral analysis of this Lindbladian, which we can vectorize in the form, and then see that which are the eigensectors are being occupied by the operators. Then as we can see that, okay, for the eigenvalues are negative apart from the 0, which is the steady state, which will remain at the long time. And if we saw the scaling, which I mentioned earlier, is nothing but the summation of the, it just gives this form of the evolution in terms of this operator amplitude with the initial state amplitude. Okay. Yeah, so here are the plots of those amplitude. The green circles corresponds to the different eigensectors, the CI/OI terms, whereas the square corresponds to the total of that. And we see that apart from the steady state, the only one eigensector is being occupied, which immediately shows that, okay, the system has picked up only one time scale. And thus the universality appears in the system. Okay, I think I'm already lagging in the time, so I'll summarize. So what we have seen is that for under the SYK4 Hamiltonian, the disorder average dynamics of few body observables, including quantum fission information, and lower order moments of other local observables they show universal dynamics even in the out of equilibrium system. The equilibrium state is the infinite temperature state, and the rescale dynamics which you have seen, it can be well approximated by a Gaussian, leading to a sort of a super exponential equilibration dynamics. And the features which we have captured are generic to all the ISOIKs, and furthermore, one of the novelty is that we have devised a Linville master equation formalism in order to capture that this disorder average dynamics, which I emphasize that is not only applicable for the delta correlated noise processes, in which case earlier people used to use for the noise processes this Novikov theorem, but even for these coincident disorder systems, we could apply the formalism quite well. So thank you for your attention. With this, I conclude my talk.
Thank you very much.
Thank you.
Any questions? Okay, I have a question because it seems to be a very general result, because this kind of master equation I usually derive under strong conditions about the decay of correlation function for this noise or the reservoir. And how do you have any idea what is the range of application of
okay, okay, thanks a lot for the good question. At present, I cannot say the range of applicability, but what we understand so far is this model, specifically this chaotic nature, is allowing us to apply. Specifically, we have done two strong assumptions. One is a decorrelation assumption, which is Boré approximation, and then another one is the Markov approximation. But still, it's getting applicable for this infinitely correlated disorder, right? The Cohen's disorder. So what we understand is this is due to the extreme chaoticity of the model. So what we understand that this general formalism should be applicable for the chaotic models. That's what we think. But yeah, a rigorous estimation of the applicability, I think we have, I mean, is one of our very recent aim to perform it. So I'm sorry not to answer it right now. Yeah, so I don't know in this moment. Yeah.
other questions? This is not the case, so thank you again, all the speakers on the morning session.
Thank you.